Okay, so don't forget, Jack just pointed out the homework is due on Monday. You still have through the weekend. I'll be here in the morning, or not tomorrow morning, but Monday morning if you have any questions. Okay, so with the time we have left, I want to go ahead and just introduce these to you. I will be proving these to you next week. In fact, we'll be starting with cosine of alpha minus beta, and to date it's probably going to be one of the biggest proofs we've looked at. It's not horrible, but it also definitely does take some looking at for you to really get what it's saying. So I'm hoping to do that on Monday, but I thought we'll just go ahead and talk about these today, kind of introduce you to them, and then we'll derive them next week. So in this section, we use formulas that involve sum and differences to verify identities. So you guys think back to the original Happy Minutes. Well, for a very long time, I was giving you some kind of angle measure, and you were creating a triangle, finding all 6 of the trig ratios. Do you guys remember that? But the problem was we were stuck with those 16 values on the unit circle. Only the 16 that we were really looking at, those that were either a quadrantal or they gave me a special right triangle. How many other points are going to be on that unit circle? There basically is an infinite number, right? Not just the 16. So we're going to expand our world a little bit. What if we start coming across an angle that's not familiar to us, but we can rewrite it in terms of angles that we are familiar with? Okay, you'll kind of see that connection when we look at the final example today. But here are our 6 new identities. We've got all 3 sums and all 3 differences. Okay, so alpha and beta just represent 2 different angle measures. They could be degrees, they could be radians. Okay, it does not matter. But you'll notice there are patterns here. If you have sine of a sum, you'll notice you've got 2 products, but sine likes to alternate them. We go sine, cosine, cosine, sine. We like the 2 different trig functions multiplied together. One other thing that sine likes to do, you'll notice if you start with a sum, what happens? You keep that sum. So sine of addition, you're going to keep the addition when you expand it. All right, so if I look over here, sine of a difference, okay, well, I'm still alternating in the products. We got sine, cosine, cosine, sine. And if you start with a difference, well, you're going to continue with that difference. Sine likes to keep the same operation. Okay, but with those in mind, look at cosine. What does cosine do differently? Yeah, for one thing, Jack says cosine changes the operation. If you start with cosine of a sum, he wants to take the opposite operation. So cosine of a sum becomes a difference, just like cosine of a difference is going to become a sum. There's also one other item that changes. Okay, what do you think, Jack? Yeah, the way we described it for sine, it likes to alternate. It multiplies sine times cosine. But cosine doesn't alternate. He has cosine times cosine, sine times sine. Okay. Now, probably out of all the 6, I think the easiest to work with is going to be the tangent, even though it does create a fractional value. It's the only one that goes fractional. Okay, but if you take a look, you'll notice in both cases, tangent alpha, tangent beta, 1 on the bottom, and then a product tangent alpha, tangent beta. That's exactly what we see over here in the difference identity for tangent. It's the same pattern, tangent alpha, tangent beta, 1, product of tangent alpha, tangent beta. The only thing that changes here are the signs when you're dealing with tangent. And here's how I kind of like to think about it. If you start with a tangent sum, that carries to the numerator. The numerator will always have the same operation, but it's the denominator that changes. The denominator will take the opposite when you're dealing with the tangent identity. So over here, you'll see we have tangent of a difference. I'll carry that difference into the numerator, and then it's the denominator that changes it. Okay. Now, one thing also about the terms that you're using, we're calling these alpha and beta, their order always remains the same as you go through every single one of these. You'll notice I start alpha plus beta. Well, it always goes in the order alpha, beta, and the same thing is true for every other formula or identity that we're going to use. Okay. Now, one other thing, these rules are reversible. So sometimes you might be given, a trig function of a value and asked to expand it. like these formulas are showing us. But you might already be given the expansion, and you're going to be asked to shrink it back down or condense it to a single trig identity. Okay. Well, before we go ahead and get to an example, what patterns do you see that could help you memorize these formulas? So basically, our talking about it, well, that's really what I wrote down. The fact that sine keeps its operation, cosine does not. Sine is going to alternate with the products. Cosine is going to keep them grouped together. Okay. So I'll give you a few seconds to go ahead and write that down. Okay, and I'm looking around the classroom. The only person I think we're missing is Christian, right? He was here today, right? He's what? No, but Zach wasn't here when we first started the class, correct? I don't remember seeing him today. Was it Christian here? I could have sworn I saw Christian today. Okay. Oh, well. It's possible. Okay. It is a big building. Okay, so let's practice these identities and see what you guys think. Here's our first example. Cosine of 70 degrees times cosine of 40 degrees plus sine of 70 degrees times the sine of 40 degrees. Okay, now we could absolutely just, take some technology, a calculator, type in that expression, we'd have our answer and we'd be done. But you guys know I'm a big proponent of being able to do things as much as possible by hand, because what if you don't have a calculator and you're still asked to solve a problem like this? Well, 70 and 40, are those measures that we're familiar with on the unit circle? No, so we'd probably have a pretty hard time trying to solve it as is. I knew I saw it. Okay, so let's go ahead and identify which identity is being used here. And there's two ways that we're going to go ahead and do this. First, we need to decide, is this a cosine or a sine? Like, how do we know immediately it's not one of the two tangent? Yeah, there's no division, and tangent has tangent all over the place, right? So we know it's definitely not tangent. So let's see, what was it? Which one does like this one? This one does not alternate. It's got cosine times cosine, sine times sine. Which one did that? Okay, there we go. So we know because of the pattern, the way we're multiplying, this has to be cosine, right? And the order in which you're given the values never changes. So that's got to be alpha, and that's got to be beta. So I know I'm going to have 70. I know I'm going to have 40. And what is one thing that cosine really like to do? He changes the sign. So if the expansion has a plus, I know there has to be a minus right there. Now, what is 70 minus 40? 30. And is 30 an angle that we're already very familiar with? Yes, we don't need a calculator. We can absolutely take care of that by hand. Okay, so what quadrant would 30 degrees be in? Quadrant 1. So I'm going to draw a terminal side right here. Here's 30 degrees. Connect it to my x-axis. Now, think back. This is the unit circle, okay? One of two ways we could do this. We know that the radius is always 1 because we're on the unit circle. Does anybody remember the side lengths for this particular triangle? Aiden? Okay, she says the one opposite 30 is 1/2. Square root of 3 over 2. Yes. You remember saying that or the 45-45 triangle over and over? Okay. Now, even if you didn't remember, the 1/2 and the square root of 3 over 2, it's still a special right triangle, so you could work backwards from the 1 and still get those. But what is cosine's ratio? Remember, it's always x over r, right? Okay, well, the x value here is the square root of 3 over 2, all divided by r, which is 1, but what's anything divided by 1? Yeah, so it's just square root of 3 over 2. Okay. So we were still able to simplify this whole expansion, that whole problem, by using the identity. And sometimes that's what you'll be asked to do. You might be asked to condense it, or you'll be asked to expand it. And that's what these next two are doing, A and B. We've already been given the expansion. We have to decide, is it sine or cosine? Is it a sum or a difference? But on these two, we are not worried about solving them. We're just applying the identity. Okay, so take about 30 seconds, if you haven't already done so. See if you could take these A and B expressions, pull them back down to a single trig function. Sine or cosine of what angle? That's what we're looking for. Okay. And remember, the order that those angles are given, we always like to keep those the same. So in this case, what's alpha? 22. The beta is going to be the 13. Okay, good. Okay, so let me catch up to you real fast. So I'm looking at A. I see that it alternates. A product is sine cosine. So I'm going to come on over here. Which identities do that? Is it sine or cosine? Sine likes to alternate, right? So I know this has to be sine. Okay. But does sine change the operation or keep it? Sine keeps the operation. So I know that this plus, I'm keeping it. So I'm going to go ahead and put 22 and the 13. So this actually is equivalent to sine of 35 degrees. There we go. How many people got that right? Okay, good, good, good. Let's try the next one. What do you notice about the pattern? Do the products alternate or no? No, it's cosine, cosine, sine, sine. So if they don't alternate, it's got to be a cosine identity, right? Okay. And what does cosine like to do? There you go. So you'll notice this was expanded using addition. So I should put subtraction here when I bring it back to a single trig function. Now, what should I put? Pi over 3 minus 4 or pi over 4 minus 3? Pi over 3 minus 4. Remember, the order is very important. We're going to keep that the same. Okay. And then all we have to do is just a little bit of algebra to figure out what that is. What's my common denominator? Okay. So pi over 3 minus pi over 4. I would have to multiply this by 4 over 4. Multiply this by 3 over 3. So 4 pi over 12 minus 3 pi over 12 will give me 1 pi over 12. So cosine of pi over 12 is what we're looking at. How many people got that one right? Okay. Now, it doesn't really expand our world a whole lot, but I'm hoping you can kind of see, what the benefit of these identities are going to do. Like, for example, at the top of the next page, what if you were asked, okay, I want to go ahead and simplify or solve cosine of 15 degrees. Well, the first thing we think, is that one of the 16 angles that we're accustomed to? No, but could we rewrite 15 by adding or subtracting two angles that we do know? You see right here, we used what? 45 and 30. And see, we know how to manipulate these at 45 and 30, so we could easily figure out that problem. We still don't need technology. This is also going to be very useful to us when we continue to use the identities and we simplify and prove these equations. We now have 6 additional ones that we can use. Okay, so is everybody kind of starting to see the idea? Okay, so this is what we're going to go ahead and start with on Monday. We're going to go ahead and stop here. I'm going to use this problem to begin, and then hopefully after the homework we'll have enough time for the proofs, and we'll see how far we get. Okay, good.